Greetings, geologist, and welcome to Section 4, Minerals and Age Dating. Today we're going to learn a lot about how minerals are classified, why they look so different yet similar, and then how do we date rocks? What are some relative dating techniques? What are some absolute dating techniques using isotopic dating? There's one key concept from the get-go that I need you to be very familiar with, and I can promise you it's a test-related question. Minerals make up rocks. Rocks don't make up minerals. What do I mean by that? So if you take a piece of granite, it can contain, let's say it's pink granite, it will have potassium feldspar, which makes that pink color to it. It'll have some black, which is biotite. It'll have some milky colored material and some white colored material, of which could be things like other feldspars, orthoclase, and quartz. The point is, there's a hodgepodge of accumulation of various different minerals that grow together to make that specific recipe of granite. So granite comes in numerous color mixtures, and that's because it has different minerals present in them. So granite's not a mineral itself, it's made up of minerals. It is a rock. There are a few minerals that have the name rock in them. For example, people give a common name to rock salt. Well, really, it is salt. It's halite. So understand that, don't be deceived by that name if it has rock in the mineral name, like gypsum rock. It's really still a mineral. And gypsum can be found in rocks for sure. And then gypsum can be found by itself. So let's get into how we define minerals, how they're different, how they're similar. Another important definition for minerals is this. Minerals are naturally occurring inorganic solids, and they have a very specific, definite chemical composition, and I might add order of atoms. So every mineral has its own recipe of elements that are arranged in a very specific manner called a lattice. So another important definition for you to know about minerals is that it's a naturally occurring inorganic solid with a very specific, definite chemical composition. That chemical composition and the arrangement of the atoms inside of that mineral is called its lattice. So there are over 3,800 known minerals that are naturally occurring on Earth, and more are discovered as people are researching, doing field studies, and so forth. Don't confuse naturally occurring minerals with minerals that are grown in laboratory type of settings. So the picture you see before you is halite, which is salt. Some people refer to halite as rock salt. Well, don't be deceived by that name, rock salt. Halite is simply halite. It has a very specific crystalline lattice of the atoms that make up the various different sodium and chlorine parts of your atoms to come together to make that perfect combination that creates halite, which gives it a special taste, a special appearance, crystal shape. It even gives it a special cleavage, things of that nature, which we'll be learning about in just a minute. So remember that minerals make up rocks, rocks don't make up minerals. How does that work, and what do I mean by that? So let's start backwards and work our way back to the original atoms. So if you're walking out in nature and you see a layer like this one right here, it's this rock called sandstone. Let's just say it's quartz sandstone. That means it's got a dominance of the mineral quartz in it. Well, this mineral right here, these little crystals or clasts that you see here, are quartz crystals. Well, quartz is going to be made up of oxygen and silicon, which are the atoms, and the arrangement in that crystalline lattice is what gives us the special, unique characteristic of quartz. So some quartz grows in special long crystals that are real beautiful, and other quartz does not. It depends on the situation of how minerals crystallize. So that's another important thing to share with you, is that minerals all melt and crystallize at different temperatures. That is why it matters on how we generate minerals. That brings me to how do we make them. So probably the most common way we make minerals is through magmatic processes. What I mean by that is an igneous molten rock. So we got magma. So magma or lava magma being crystallized material under the ground and lava at or near the surface. The length of time it takes for minerals to crystallize, to harden, to turn into not being molten but solid, varies if you're underground or you're above ground. So if you're in a magma chamber 50 miles beneath the earth, it may take a lot, well, it will take a lot longer to crystallize that mineral than if you have a lava flow on top of Hawaii. Point being is that the temperature of the magmatic material dictates what specific minerals are capable of being crystallized. In addition, that magma chamber has a special recipe of certain minerals that have been melted to create that magma chamber. We'll get into that more in our next section, section 5. So let's look at the two ways here that we're showing you on how minerals are created. On the left side, you have a geyser in Yellowstone National Park in Wyoming. Well, as that geyser erupts and thermally heated water comes into the surface, it's going to pull up minerals that are inside of that geyser, and Yellowstone is super rich in silica-based ash, like rhyolitic ash. And so that heat combines with that silica and creates a new mineral called geyserite. So that's another way we can make minerals. On the right side here, we're in Death Valley National Park in California, Badwater Basin, kind of a hot place, a really hot place actually in the summer. The white stuff all over the ground is halite, so that's salt. So how did it get there? That's a good question, because it got there because there used to be some type of water body and it was salt enriched, and so like a saltwater, literally ocean marine setting. And as that water evaporated, it left behind the solids known as halite. So those are called salt flats. Some areas people like to call salt rock salt, but don't get caught up on that term rock. Remember, minerals make up rocks. Rocks don't make up minerals, and halite is a mineral all by itself. So what if I have a variety of different minerals? So all of these minerals you see right here are from the Smithsonian Museum of Natural History in Washington, D.C. And on the left, I have opal. Opal's such a fascinating mineral on how it forms. Then you've got a special type, there's some calcite. That the stuff right here is calcite, but the purple stuff is something very different. You would know that as a precious gemstone. I bet you can guess which one it is because lots of people like it. Then we got some quartz crystals, and we got a zircon over on the right. So how do I know this besides the fact that some of them are labeled? I would be able to do some testing on minerals and look at some of their special properties. Without having a scanning electron microscope, take literally a sliver of that and put it into a powder form and then examine it under a microscope and get a reading of what elements and atoms are in there, you have to rely upon mineral properties to help you identify what they are. So mineralogists are the people who do that. They are scientists who study, identify, and classify minerals into specific groups. You know that there are people who are gemologists, who are experts in gems. And gems are minerals, but many minerals would not qualify as gemstones. So don't confuse the two people. They may not have the same training. So a mineralogist, if you decide to go into geology as a major, you'll be taking a couple of classes in mineralogy to learn how minerals, their special properties work, and really dive into understanding each of those properties and identifying them in hundreds of minerals. So what are some of the ways we identify minerals? We'll be going through all of these. Mineral color is obviously one way. So if you looked at this mineral right here, which is a relative of quartz, and I bet you're like, I know what that is. I got to think about what that is, the purple stuff. Well, color would be an indicator, but don't be deceived because that mineral can come in more than one color. So color, we're going to get to, is not the best. And we'll look at its streak color. We'll look at hardness, very important property, luster, specific gravity, cleavage, fracture, crystal shape, and then some various special properties that are unique to just a handful of mineral groups. Let's talk about color first. That's the first thing people see when they observe and look at minerals. Here's the deal. This is all calcite right here. Well, if it's all calcite, how do you tell it's calcite? There's got to be a better way. So there are a few minerals that actually only come in one or two colors, and color can be super valuable in identifying them. For example, azurite is a kind of a bright bluish color, and that is a very notable color that you could say, hey, that might be azurite. So if that's the case, that would be useful, but it's not the case for a majority of our common minerals. There's literally about 20 to 30 common minerals on the planet, and the rest are fairly rare. The more rare the mineral, obviously the higher the intrinsic value. So calcite, let's be frank, it's everywhere, and so it does not have nearly the same value as something that would be extremely rare. And rare things might be like a diamond. While diamonds are common in the world, gemstone quality diamonds are hard to come by. So let's examine streak as a mineral property. First of all, streak is much more dependable than color. Here's why. A mineral may not streak the color that you may visibly see. For example, if you were to take a streak of gold versus a streak of fool's gold, known as pyrite, pyrite would streak kind of a greenish black color, while gold would have a goldenish gold color. So back in the old days when there was a gold rush, these streak plates would have been very valuable. Streak plates come in two colors, white and black. So many minerals have what is called a colorless or translucent streak, and that's why we have black streak plates. Many minerals have a color that are very specific to helping identify a mineral's category or its name. So there's a book that we can use that is called the Audubon Society of Rocks and Mineral Guide. I used to make all of my students buy it, and I have some here in the classroom if you'd like to look at them. And if you're in a face-to-face class, you will be using them. But you can actually find all the information you need about every mineral there that's common. So let's say you're in an online class. You can go online and look at streak color for any mineral and just do a Google search, find a reputable website, preferably, like the Association of Mineralogy, something along those lines, and be able to identify what streak color is for all the minerals that you'll be testing in lab. So streak is a really important test. So if I could turn the clock back and go back to the rush days when the people were out there looking for gold in California and Alaska, I would have taken a streak plate with me, and I also would have been testing for hardness. Well, speaking of hardness, let's look at the mineral property of hardness that's measured by the Mohs hardness scale. The Mohs hardness scale is a relative hardness scale. So in other words, going from a hardness of 1 to 2 is not 10 times harder. It is relative. So it's not a logarithmic scale. Hardness measures the strength of a mineral in terms of its ability to be resistant of scratching. So the lower the number, the more prone to scratching it will be. So that could be scratching from another mineral, that could be scratching from a human tool, such as a nail that you would hammer into the wall, a steel file, it could be a knife, it could be a penny, it could be your own fingernail. There's a lot of different reference points that we'll be looking at. So, obviously, if you look at the Mohs hardness scale on the right here, as I mentioned, there are 10 reference minerals. So all 3,800 plus minerals have a Mohs hardness, but these are the very common ones. In other words, they're minerals that are common throughout the Earth's crust and at the surface. So when we're looking at the Mohs hardness scale and the 10 reference minerals, diamond is a 10. It's the hardest substance known to man. And it should scratch corundum. So what is corundum? It has a number of different forms, and you may find corundum to be something like a sapphire or a ruby. Then there's topaz. So corundum cannot be scratched by diamonds, but corundum could certainly scratch topaz. Topaz has an 8, so it should be able to scratch quartz of a 7, and topaz would not be scratched by quartz, but it would be scratched by corundum. So you get the gist. So of these minerals, when you start going through like to feldspars or orthoclase is a general term for all kinds of feldspars, and feldspars make up our clay. And a lot of our feldspar minerals come out of igneous rocks as they weather and fall apart. So feldspar is a 6, and so certainly be scratched by quartz, but it would not be scratched by apatite, which is a 5. So apatite could scratch fluorite, but fluorite cannot scratch apatite. Fluorite will scratch calcite, but calcite can't scratch fluorite. So if I have, you get the gist here now, gypsum and then talc too. By the time you reach gypsum and talc, you should be able to scratch it with your fingernails if you are not a baby with really, really soft fingernails. So meaning like a child, like a little infant, they have very soft fingernails. But as you look at these, there are a couple of minerals that I think are really important for reference minerals. That's quartz would be one of them. It's super common. And then calcite is another. And the reason being is very, very soft minerals. By calcite, you may or may not be able to scratch that with your fingernail, but you would be able to scratch it with a regular nail that you would hammer into the wall. And so that becomes an important reference mineral. So quartz can scratch 6 through 1. And so if you can scratch something by quartz and you find a piece of quartz, then you kind of know that you're looking at a softer mineral. But if it won't scratch anything that you have, if quartz won't scratch a sample of a mineral, then you know you have something with an 8, 9, or 10. So a question I often get from students is, well, can quartz scratch quartz? It is remotely possible that one piece of a mineral could have just enough slightly different properties that it could scratch a similar mineral of its kind. Typically not the case. And how do you figure out that you have hardness differences when you're doing a hardness test? Because when I see students do hardness, oftentimes they just take the glass plate, because you'll have a little glass plate in your testing equipment for minerals, and they just kind of do this action. Just a real quick movement of that mineral over the glass. You've got to dig it. I mean, really dig into that glass or into another mineral. And then you wipe away the residue. And if there is a groove or gouge left behind, then that mineral scratched whatever you scratched with it. Or if what you scratched left a groove on your mineral, that means that your mineral was softer than whatever you struck it against. So be really cautious in that. I have an explanation in the book that's very thorough about how do you interpret hardness. So you're looking to see if that powder residue, once you wipe it away, if there's a little gouge left behind. And if there is, then you know you have a mineral that's harder. So oftentimes when you find quartz, especially for your harder minerals, you'll use those minerals against each other, and when you finally find one that scratches quartz but can't scratch corundum, then you know you got topaz. When you find corundum and it scratches everything from 8 to 1, you know you found corundum. So I'm going to be frank, there's not going to be diamonds in your box when you sample in lab, but there will be all the other general minerals and a few more. When we're thinking about hardness, there's some good field tests that we use to try to figure this out. So when I go out into the field, I always have a few things I take with me. I take a penny, I take a pocket knife, I take a little glass plate, I take a street plate, I take a steel nail or a file, like a nail that you would hammer into the wall, and then I always take a piece of quartz with me. Another thing I take with me is a little bottle of diluted hydrochloric acid. So it may sound a bit nerdy, but nevertheless, that is very common for a geologist like myself. So this mineral you see right here is a sample I have in class. It's a sample of gypsum. So the scratches on the outside there, like right here, I was able to do with my fingernail before I took this picture. Or I could have used any of these tools and it would have left a gouge behind. But remember, I need to wipe off the powder residue, because students often confuse if there's powder that said, okay, well then it had to be harder. Which one was harder? And it can be confusing. So you have to wipe it clean and both surfaces, and then look to see if what you use the mineral against has a gouge or if the mineral itself has a gouge. And that will help you to delineate its hardness. So let's look at hardness on two substances, again, from the old gold rush days that I think would have been a valuable thing to know. So if you could turn back the clock and go pan for gold and make your living that way, first of all, you'd want a street plate. Second of all, you would want to do a hardness test on every sample you collected. So pyrite, which is called fool's gold, and from this day forward, the only thing I'm going to allow you to call it in class is pyrite, has a hardness of between 6 and 6.5. So that means it's like a feldspar hardness. Not quite quartz. So quartz can scratch it, but apatite wouldn't, because that's a 5 on the Mohs hardness scale. Nor would a copper penny or any kind of penny scratch it, or your fingernail. But gold, however, has a 2.5. So yeah, it can be scratched by a penny. It's much, much softer. So let's go back to our field test again. Your fingernail should be about a 2.5. Now, if you have nails that are made with acrylics, they could be slightly harder, obviously. But most of our pennies are about 3.0 on the Mohs hardness scale today. So your pocket knife will be somewhere between a 5 and a 6.5. You're like, that's a big difference. Well, it depends on what the alloy was that was used to make your particular knife or steel nail or steel file. So all of those things factor into it. The point being is that hardness would be very important for determining if you have something worth a lot of money like pyrite. Hardness would be super important for determining if you have something super valuable like gold, or if you have something that's just pretty and has a small intrinsic value like pyrite. So knowing a mineral's hardness is important. Knowing its streak is important because it helps differentiate between minerals such as pyrite and gold. So what is luster? Luster is how a mineral reflects light from its surface. There's lots of different ways that a mineral can do that, but there's two primary broad groups. There are metallic lusters and then there's non-metallic lusters. Bottom line is if a metallic mineral reflects light and it's really shiny, then that's called metallic luster. If it doesn't reflect as a shiny, like gold, for example, then it would be non-metallic luster. So there's a lot of different types of non-metallic lusters, and I put a whole table in your book that shows the same thing right here, what all the various non-metallic lusters are. And I'm going to tell you I'll just give you a handful. Dull and earthy. So it doesn't have a very good shiny look at all or clear look. It's just kind of dull and it doesn't really see well through it. That would be like limonite, a mineral that you will come across a lot. It's a softer mineral. Some of them have vitreous, and so they are very glassy looking, but they're not shiny like a metal. Or they could have waxy, where they appear to have some kind of a coating on the outside. Jade looks that way. Certain forms of quartz can look that way. So all these various different types of luster are there to describe how non-metallic minerals reflect light. So there's another mineral property that's very important, especially when you're looking at metals and metallic types of minerals. This describes how much matter exists and the amount of space that a mineral consumes. So there's a piece of galena that you see in front of you, and this piece is about this large. It's fairly large. That thing weighs quite a bit. If you picked it up with a mineral that is the same size as this, let's just say quartz versus specific gravity would go in your hands because it's so much heavier. Basically, specific gravity is a measure of how minerals relate in terms of their mass to the mass of water. So the closer you are to 1, you have the same specific gravity as water. So the higher the number you get, the denser the mineral will be. That matters because the density can also change. Like if you have minerals that are really dense and they're in rock layers like igneous rocks, let's just say you have a plate, an ocean plate that's made of really dense metallic minerals, let's just say high in iron. then that would be more dense than continental crust that has minerals made out of maybe a 1 to a 4, as opposed to minerals that are from 6 to 20. So you can kind of see how that would matter when the two plates collide. The minerals that are inside of them dictates how the plates are going to relate to one another. Cleavage and fracture. So how minerals break apart is what cleavage and fracture refer to. So we're going to go through each one individually. This table is in your book, so I'm going to move on and talk about how they are different. So first of all, cleavage peels apart into layers or breaks apart into layers like a loaf of bread, while fracture breaks and leaves some kind of a non-flat surface line on that mineral when it breaks apart. So I'll give you an example. You drop a glass bottle on the ground, it kind of leaves a mess, not just shattered glass, but a bulk of that glass could be on the ground. That's going to be a good example of fracture. So cleavage, this is some mica or muscovite of mine that I took a picture of, and if you look and see how it peels apart into layers, that's a great example of cleavage. So there's a lot of different types of cleavage, and minerals can literally break apart in multiple different plane directions, so that gets really complicated into mineralogy. But for this class, we're just going to basically describe cleavage as its tendency to break apart along specific planes that make smooth, nice surfaces. So mica would be a superior choice for looking at cleavage. When we think about fracture, however, fracture is different. They don't break along those nice clean lines, and they break apart in an orientation that's not the same as its cleavage. Not all minerals have cleavage, by the way, but all minerals have fracture. And so people are like, oh, it's so confusing. Well, it can be. So this may have some cleavage, like I could see that it could break apart here, but you see these rough edges here, that would be some of its fracture. So irregular fracture, folks, is the most common type of fracture that exists. But another type of fracture that we see a lot of, especially in rocks like you see here on the right, which is obsidian, volcanic glass, is called conchoidal fracture. So my dad was a surgeon, and he used, some of his surgical tools were actually made of obsidian because of how it fractured and how durable it was. And it's really sharp. So if you're handling fractured specimens of material, be careful, especially if it has a conchoidal fracture. I've made one trip to the emergency room to have stitches from handling obsidian, which is volcanic glass, because it has a conchoidal fracture. All right, crystal shape. So this is one of the fascinating parts about minerals when you study them. When you take mineralogy, if you become a major, this will be something you look at a lot in mineralogy. So when minerals have the opportunity to grow, time to grow to be specific, they contain time and space. They can start to grow and extend in the internal crystal lattice from its original position and grow outwards. That's what a crystal is. That's all it is. It's just space and continuation of that same atom structure in a lattice. So you're just repeating the cycle. So even minerals may or may not grow into a crystal if they don't have the space to do it or the time to do it, or both. So crystals can change their character based on both of those factors. Even the same kind of crystal, like calcite, can not be in a beautiful crystalline form, or it can. And same thing with quartz. So here's a zircon here. I showed you a zircon earlier. It didn't look like anything like this except in color. And then here is another mineral, and different types of crystals. As you look at them, that's pretty awesome that they make these different shapes, and that's all a result of the lattice of the atom structure inside of that mineral. So what are special properties? These are things that minerals do, or properties they have, that set them apart from other minerals. So let's look at the left picture here. This is a piece of magnetite that I purchased in Springdale, Utah. And that there's a rock shop there. It's kind of a funny story. Early on in field course days, when we first started going, I had a small budget to buy some stuff for geology. And I walked into this shop and played like I didn't know anything and caught them selling some fossils that were claiming to be dinosaur fossils, which were nothing of the sort. And so I basically could buy what I wanted at face value. And that's how I got this piece of magnetite. And the piece is huge. I mean, it's literally more than a foot tall. And it should be a very expensive rock, and I bought it for 15 bucks. I'm pretty proud of it for my $15 investment for this piece of magnetite. So I stuck some magnets on it, and you can see they're sticking without me gluing them. That's because it's magnetized. That is an example of a special property. Some minerals will fluoresce. In other words, like these right here, fluorescent minerals glow when they're placed under an ultraviolet light. So a lot of minerals that just look plain and dull, like calcite, for example, many forms of calcite will actually fluoresce under those conditions. Fluorite, aragonite, apatite, zircons, they can all fluoresce. We talked about magnetism. Reactivity is another one. So if you get a sample of calcite, the very first thing you would do is squeeze acid on it. So I'm going to go get some acid right quick. I'll be back in a second and we'll try that. All right, so I'm going to try and show you what reactivity looks like after death. So I'm going to show you what reactivity looks like, and you would use some diluted hydrochloric acid and you would drop it onto your specimen. And if you can see it's sizzling, it's having a reaction, that is reactivity. So there's only one mineral that does this, it's calcite. So I'm going to use a few more samples, just see if this one does it. So it's doing it again, that means that's also calcite. You can see that right there. And then let's try this mineral, looks a lot like the others. Nothing is happening. It's just gonna, the acid's just gonna go right off of it. Well, that's because it's quartz and it doesn't react to acid. So again, the only mineral that you would have that would react to acid is calcite. So you may put acid on a rock and it react. It does not mean that the rock is calcite. It just means the rock has calcite in it. A common mistake that students make in sedimentary rocks is they assume that everything that reacts is limestone, and that's not necessarily true. It just means that the rock has calcite in it. Another thing you'd want to do is smell rocks. I joke you not. Take a whiff, and some minerals have a distinct odor. Let's say sulfur, for example. Stinky, and you'll know right away. Another one is taste. So this is a common mineral that we would use to taste. This is the way I taste. And tastes like salt because it is. It's halite. Some minerals have a bitter taste. There's actually a mineral that would kind of make you foam at the mouth, or if you want your dog to look fierce and ferocious, you just let them lick it and it'll scare everybody around them and they'll go away, they'll be fine. But I'm never do that to a student, so I was one of those people who had that happen, and I took my first mineralogy type course, and I of course volunteered to be first, and I hadn't read all my assignments from the night before, and the teacher put out something that is a mineral that looks a lot like halite. So, but when you taste it, it is super bitter, and you start kind of have this bitter taste in your mouth. Awful. So just know that taste is an important element. So I'm okay with doing that kind of stuff, but that was strong. Very, very salty. But I realize you may not be, and if you want to watch your specimens, have at it. But I would encourage you to start tasting things. When you're in the field, do that taste thing and see if you don't get a hit, because it'll help you narrow the scope of what that mineral could be. So let's show you that effervescence again. So let's show you that reactivity again. So I did a piece of limestone, and you see the reactivity there if you couldn't see it on my other samples. And here's that odor if I were to sniff that piece of sulfur there, it would stink like rotten eggs. So that's a really, really good way to determine what you have. And certain minerals have these properties and most do not. That's what makes them special. All right, so now that you know about the properties, everything from color to special properties, we apply that knowledge, and then we need to learn about how minerals are grouped into major categories. For silicates, there's two categories, ferromagnesian and non-ferromagnesian minerals. Those that are ferro, that's a good indication. They have iron and or magnesium. The non-ferro, because ferro meaning the ironish type and magnesium-based minerals. So ferromagnesian tend to be darker in color and more dense than non-ferromagnesium silicates. So these lack the iron and magnesium and are usually lighter in color. So what are some examples of non-ferromagnesian minerals? Quartz would be your case in point. So this is a good piece of quartz right here. This is potassium feldspar. And plagioclase feldspar looks just like this. It's just kind of a milky white color. Muscovite, which is this stuff right here. Then your ferromagnesian example. So this right here is olivine from olivine basalt. That's what this is right here. Biotite, which is a blackish mineral that you'll find in granite, and other types of dark minerals like hornblende, pyroxene, stuff like this would be your ferromagnesian type of minerals that are silicates. All right, let's move into carbonates. So the reactivity will be important here because carbonate minerals contain a combination of carbon and oxygen mixed with other elements such as calcite. So this is some calcite from the Smithsonian Museum of Natural History in Washington, D.C. So calcite will react to acid. However, dolomite typically will not unless you have it squashed up into a powder form, and even then it may not because it's got more magnesium. It's got one molecule of magnesium in it, and so it makes it a little different than calcite. So carbonate minerals are formed in a carbonate setting, typically in marine environments, or certain types of lakes can produce it, but most commonly in marine salty environments. All right, what are halides? Halides contain elements like chlorine and fluorine. So halite, this mineral right here, the salt that I tasted, that would be a halide, and fluorite. So early on in my teaching career, I had an incident happen with some students, a boyfriend-girlfriend pair, who were in a lab group the day that we returned back from the holiday. So it was a Monday, Wednesday class. So we had Monday off for Labor Day, and they came in on Wednesday to do their first mineral lab. And all the students are learning how to do streaking, what hardness is. So they're using all the tools like a steel nail to gouge against all of their specimens and putting acid on their specimens, all of those great things that we do in mineral testing. And this guy had bought his girlfriend an engagement ring and given it to her on Labor Day. So she had said yes, and she had this ring, and she decided she was going to do a hardness test on it. And she took the steel nail and she went, and a giant canyon got left on that ring. And you could see this, ooh, lookable. The guy was just mortified. He had paid several $1,000s for the ring and had been totally duped. He had a sample of fluorite. But there are diamonds that are very rare that come in different colors, even the ones that look like fluorite. So here's what happened. The girl threw a ring at him, said, "Oh, you got me this cheap ring. Is that the kind of wife you think I am?" And just ran out of the class, took her, threw everything down and took her personal stuff with us and never returned to class. She dropped the class that day. So he is left in mourning. I tried to help him. I went with him to the jewelry shop and we worked on getting his money back for the ring because they totally scammed and they knew it. So they gave him his money back in full. But he still had no girlfriend. So he became friends with one of the girls in his lab group who helped console him through this time. They ended up getting engaged and married. And at the top of their wedding cake, they put a piece of fluorite on the top of their wedding cake. And I got to go to their wedding. So it was a lot of fun, and halides can be fun, and they are interesting minerals, but I wanted you to have that fun story. So please, when you're testing your samples, do not test your jewelry. I don't want to find out that you have a mineral that you don't think you have. What are sulfates? Sulfate minerals contain sulfur and oxygen combined with other minerals. So these are a thing of barite. I have some of this in the classroom, and these are beautiful specimens. These are from the Smithsonian. And then you have gypsum. So gypsum's super common. It's an evaporite. And then barite, while it's so beautiful, people are like, how does it form that way? It's just the crystalline lattice. It's just how it forms. It's the mineral of barite that makes those beautiful looking crystals. All right, sulfides. These are going to be metals such as galena and pyrite. So like if you put acid on galena, it typically produces an odor, like a stinky odor, and because that's that sulfur coming out of it. So sulfides tend to be more dense than some of the other minerals in terms of its weight, its specific gravity. But when you're testing them, and you smell that stinky stuff, if you're using the diluted acid, that's probably what you're smelling is a reaction with the sulfide. Then there's things called native elements. So native elements include copper, silver, gold, and diamonds. So this is copper, this is some natural silver, this is my wedding ring, so it has gold and diamonds in it, so it's just use that as an example. So these are important elements, obviously high in intrinsic value, and they are sought after for obviously monetary value and for building and industrial reasons. The most common way to date rocks is by relative dating. And relative dating does not use formal testing like isotopic dating to do it. Instead, we use similar rocks nearby that are age dated or have been chronologically sequenced in a geology map. And geology maps are very colorful. They are the colors represent different eras and periods of geologic time. For example, grains are associated with Mesozoic aged rocks. So I would not expect ever to find this fossil in a layer that's designated as a green on a geologic map because trilobites went extinct before the green layers were ever made. However, I would expect to find my beautiful ammonites here in those green layers. So relative dating can be very useful because it's kind of like going back to what I was talking about with key beds early on in the semester. We're looking for a basic sequence of rocks, and so strata, we can use those rock layers that have little clues in them like fossils to help us determine the relative ages of rock. There is a second type of dating that's certainly more precision-based, and it's called absolute dating. Geologists primarily use this type of dating, and it's isotopic dating, to determine the more precise age of rocks. And when we're doing isotopes, we're looking for unstable radioactive isotopes. Mineral-specific elements, lava and ash deposits, very good sources for age dating. And even certain fossils can be used for absolute dating. But it's all done on something called a half-life. So what is a half-life? That's the time needed for a radioactive substance to reduce its atoms by half. So you start with, let's say, 100 atoms, and then you go down to 50. That would be a half-life. So if we're looking at a half-life of this particular substance or element known as phosphorus-32 to sulfur-32, it takes the half-life of phosphorus-32 to become 14 days. So at 14 days, we would have lost half of the original atoms. So now we have what's called daughter atoms left over. Fancy thing, but all it does is help us determine how long those are. And so kind of a cool issue with isotopic dating. It's used in crime lab dating. For example, if we get some DNA or something left at a crime scene, or let's say a deceased victim, or you have some kind of a footprint or something that's left behind that can be age dated. Some of these have very, very short half-lives, like hours, and so it can be important isotopes for measuring the length of time when something went away. So carbon dating is probably the most famous that people come into this class with. They're like, okay, well, carbon dating means that it can be applied to any rock. Well, you can certainly do the test on the rock, but you're not going to generate it on anything much more than 50,000 years in age, and here's why. The half-life for carbon-14 is 5,730 years. So that's a commonly accepted number. You'll find some references to a bit more, a bit less, but 5,730 is what we're going to use for this class. So a half-life of that, you can imagine, would be, if that's your half-life of something with carbon-14, that means you can't have something that is multiple, like 100,000 years or certainly 1,000,000 years older, because you're going to run out of the carbon-14 to even have enough to measure. So that's the whole point of isotopic dating. So on the left here I have a trilobite. The trilobite would not be a good fit for carbon dating. It's just too old. But my mammoth tooth on the right, you bet. My mammoth tooth literally is around 30,000 years old, and it should have enough carbon-14 left in it to do carbon dating. So carbon is not a good fit for older rocks, things that are beyond that 50,000 year mark. Potassium-argon dating. Potassium-argon dating is very common. We use potassium-40, and its half-life is 1.2 billion, as in Bravo, years. Students are like, well, how do we know that? If nobody's been around for 1.2 billion years. Well, we can do computer modeling, first of all, and then we can see how few daughter isotopes are left after a certain amount of decaying time, and that's how we figure and calculate out the half-life of potassium-argon. So in this case, this particular test would be the appropriate use for the trilobites in this rock right here, as opposed to my mammoth tooth, because it's dating older materials. There's an even more appropriate test that can be used on some of the oldest rocks and even meteorites that we find on Earth. So we use uranium and lead isotopes, specifically uranium-238 that decays into lead-206, and the half-life is 4.47 billion years old. So you can be dating some of the oldest stuff in the solar system with this. And one way that we do that here in rocks that are terrestrial for Earth is we try to look for a specific mineral called zircons. And this is a zircon mineral from the Smithsonian. And zircons were made early on in the Earth's history when it was still really molten and started to cool off. And so zircons are some of our first sets of minerals that we have. And they've been recycled over and over and over. And so typically in a zircon mineral, there'll be layers of sequences of events of changes when you're doing the dating. So the key points for minerals. Minerals make up rocks, rocks do not make up minerals, and all minerals crystallize at different temperatures. They also melt at different temperatures. Their unique lattice and arrangement of all of those minerals is what dictates if it looks like something like this, or it might be this right here. Mineral properties are used to help identify specimens of all different types. So remember to do your other special properties such as streak, hardness, magnetism, special properties to help narrow the scope of what that mineral could be. And there are those 6 major groups of minerals that we use to classify all minerals known to man. So I did the best job I could on getting this to show up well. I have to keep in mind the Hope Diamond is a moving specimen, so they have it on a turntable. And it was really crowded when I was at the Smithsonian to look at this. But the Hope Diamond would have a hardness of 10. It's a very large diamond, it's very special, and diamonds require an unusual set of circumstances to form. Remember that minerals make up rocks, rocks don't make up minerals, so I thought I'd share with you an example of how minerals do make up rocks and a fascinating way that minerals can impact rocks. So I'm about to show you a geology moment of the day called Moriaki boulders from the South Island of New Zealand. And these are very unusual formations. And as you look at them, I want you to concentrate on some of the mineral properties that I talk about in the video and understand that these rock materials had been changed by mineral growth inside of them and has actually transformed these rocks into new material. All right, we are at Meraki Boulders, the beach anyway, where at least 50 of these boulders that you see in front of me have fallen out of the hillsides and been deposited on the beach. And I'm just going to kind of scroll through the beach line, let you see some of these. We'll go visit some of them up close and personal shortly. A whole cluster of them right there. And stay tuned for how these things are formed shortly. So the large boulders take about 4 million years to form, where these smaller boulders like you see in front of the big one here take about several 100,000 years to fully accrete and turn into these large accretion shapes that you see. Quite frankly, this used to be the remains of dead plants and animals and fish and other types of marine life that existed when these rocks were made at the bottom of the ocean. Keep in mind they're shales, mudstones, siltstones, but the replacement process has totally removed the fossil content and turned them into another rock. From what I can tell here without doing any testing, it looks like there's quite a bit of calcite on these rocks. Did a field test to see how hard they were, and I could almost scratch them with my fingernail and could with a penny, American penny, which tells me that they are calcite. But I also couldn't scratch some of the insides of them that were harder. So my guess is some of these are silica. This is very much almost like chert. So it's replaced the entire rock with some type of a cementing agent and created these large spherical features that got fractured during that mountain building event we talked about. Alright, how these boulders are formed is really kind of a multi-step process, but these are actually bottom of the ocean sediments from the Cretaceous period and early Paleocene epoch. And this area was covered with a shallow sea towards the end of the Cretaceous, and these represent mudstones and siltstones that were deposited at the bottom of the ocean. Now the cracks that you see on these things happen later. Happened in a mountain building event that we'll cover in class. That's actually fairly recently, about 30 or 40 million years ago. And the whole area was uplifted due to this mountain building event, orogeny, and caused these little guys to fracture. And then they got in the ground, they got saturated with water, and calcium carbonate was precipitated out of these rock layers and deposited in the cracks. And that's caused all these funky patterns that you see on these rocks to develop. Once natural weathering and erosion began to occur, these rocks fell out of the hills and rolled onto the beach. Kind of like you see this one right here, ready to fall out. So what did you think of the Meraki boulders? Interesting sedimentary material. So those ocean sediments have been changed by calcite and likely by silica and turned into more of a chert type of material, which is sedimentary rock, because of mineral accretions and mineral growth. So its structure had changed. So the chemical lattice that we talked about with the atoms had all been changed in those particular rocks from what they originally were from the growth of new minerals. So now we are to a point where you can take a break. We'll be moving into Section 5. Section 5 will cover igneous rocks, and you don't want to miss it. You're going to understand once and for all what makes granite different from other types of igneous rocks, among some other cool stuff that we'll learn in that section. See you then. See you in Section 5. Bye.